Okay, so we're back, and I'm going to finish up with this second part on implementing a more efficient swap algorithm. And there is. First, let's do a recap of what we did in the first part. Um, I explained that the very more efficient swap algorithm that we want to use deals with swapping objects that are pointer to implementation structures, and I had to explain pointer to implementation structures. Um, Got into how we have to redefine the copy assignment, copy construction, and destructor operations with pointers and classes. And and the other part was getting into exception safe code. And I gave an example of how we had our class's copy assignment operation be exception safe, and I even managed to show how I produced an exception um, off of a copy assignment operation, and I was able to have the strong exception safe guarantee occur, which was to have the original state of the program before the function executed be kept. And here we go. Now that I've kind of laid the groundwork for um, explaining explaining the things that go into the more efficient swap algorithm, I'll actually explain the more efficient swap algorithm implementation. And then after that, there will be one other part that will help tie things together. We're going to see a bit of a real life scenario of using a more efficient swap algorithm, and there actually will be a exception safe aspect to it, so you can see how everything is kind of going to be tied together. Um, okay, moving right along. Let me start by looking at our first um, swap algorithm. So I did a couple things. First, I uncommented this section, um, which is the console code, the actual client code that I'm going to be running after I explain everything. And I uncommented these very large ints, which I used to create the exception in part one. Um, Here is the first thing, the first more efficient swap algorithm. It has class arguments in it. Um, so what this is a total template specialization. I can't say specialization. Um, but what it does is it says for the generic standard swap function, which is a template function, we're going to completely redefine what it does with or when the generic type is widget. And what happens is we have a widget type called a call a member function called swap on B. And this is a new thing, and I will explain it now. Um, Here we are inside of the widget class's blueprint, and we have the member swap function. I'll get into explaining why this is used, but that comes a little bit later. So what we do here is we're swapping the pointer to implementation, which is a private variable, with the other widget's pointer to implementation. So we could originally, or we would originally perhaps want to say standard swap a p-impl with b p-impl. But because the p-impls are private members, they cannot be accessed outside of widget class objects. So that's why we're having a member function that does the swapping of the private members. And a quick rundown of why things are private is because we want to keep our code as encapsulated as possible. The less encapsulated the code is, the more susceptible it is to bugs. And basically, we don't want to give any way for client code to rely upon implementation objects like p-impl. So we make it private and inaccessible, and thus when we change implementation, then we won't have client code that relies upon it, and we won't have bugs happen when we're developing. So that's that. Okay, moving on. Now we're going to get into trying to have a more efficient swap algorithm where the arguments are template derived. And what I did for that was I made a widget class, or I made a template called thing that is basically like widget, but we can use variable types within it. And that is indicated by the type name n here. So we can have the types that are used within this class be varied based off of client code that calls for a specific type. So to explain that further, let me kind of whiteboard it. So we can have thing double called thing1, and that means that the parameter type that will be used is double based off of the template for thing. And we can have a thing called int thing2. So imagine this is client code, and what this means is that the template blueprint will create two different thing classes, one where n is double and one where n is int. And that can very simply be, let's say, represented by a blueprint, little blueprint here, and we're going to have int on it. And we'll have another blueprint here with double. Okay. So that is that. So kind of want to explain templates before we get into explaining a swap that works off of template derived arguments. And now this is the more efficient swap algorithm to use for template derived arguments. I do want to explain the ways not to do it, but let me explain the way to do it first. So basically, in the client code, anytime if there's client code that calls for a swapping of let's say thing double and a swapping of another of the same type or of the same parameter type. So once this is a part of the client code, the compiler will make sure to use this template blueprint as a way to produce a swap function where n here is replaced by double. And that of course, the way that it'll work is that it's the same as with the previous solution. The template produced class's member swap member function will be called, which is happening here. So I think that explains it well enough. And to get into the ways not to do it, I can explain it relatively quickly. So there is a thought that perhaps one could do what's called a partial specialization of standard swap, and that would look something like this, but it won't compile actually. Type name T and then swap. So this one is actually it's nice to show just because it's able it gives an opportunity to show how a partial specialization works, which is what this is. Yes. Okay. And this would be the same argument. And then we'd have our actual defining, but I won't even do that. And then we're going to close the namespace bracket. So this is called the partial specialization because we are not completely generic in that the parameter type that the template parameter type that can be changed is of a type that is widget of type T. It's not totally specialized in that the type of widget of type T can be variant. Thus, we don't have a completely generic template function here, and we don't have a completely specialized one. So it is thus called partially specialized. That explains that. Okay, and I won't whiteboard it, but the other idea that Scott Myers had in C++, or effective C++, was, sorry, I didn't explain why we can't do this. C++ doesn't allow partial specializations of functions. It does allow for classes. I don't know why, but that is how it is. The next solution, which I won't even whiteboard, was the thought of just making a simple override of standard swap. Don't have any partial specialization, and that doesn't work because we as users are not allowed to redefine the standard namespace. We can give total template specializations like we do with that first swap algorithm, because I guess we're not really changing the standard namespace. We are just we're just specializing it for our own user-defined classes. So that's that. Getting back to the code that works, this swap function for template-derived arguments. This isn't a global namespace. It could be in a specific namespace as well. And there's implications to calling swap that deal with namespaces. So I will get into that. So now let's move over to the clienting of the swap function. Here's a do something function, and it's a template as well, which is interesting. It's hard. It is hard to see the templates go on, but you gotta just remember that rule of the code, the template code, or the compiler which is doing the templating is looking for instances in the client code where the types, the parameter types that are changing exist in the client code. So then it'll make another blueprint of the function specific to the parameter types. So the method for clienting with all the ways that swap and standard swap exist now, since we have several of them, is first to do a using standard swap declaration, and then to call a call of swap without any scope modifiers on it. So there's a bit of fallback mechanisms that go on when this function is called, and I will get into that now. The best way to explain it is to look at all the different argument types that can be passed into here and result in the various swap algorithms that we know exist now. So I'm going to go ahead and show you that now. Okay. So first we made a widget, or two widgets that use our pointer to implementation structuring, which makes them candidates for the swapping. And then, or in the swapping that would be used is the total template specialization that we defined, where widgets are the arguments of the swap. Then right here we have some template derived objects, and these will, if they're swapped in client code, the function that'll be used is this one. And of course, there'll be, for however many um, template derived instances there are that of swap that exist, because it's seen um, a bunch of different thing ends existing. It could be thing double, it could be thing int. um, then those will be what is called when we swap these things in client code. So it's funny. It's like there's a lot going on here, and then I decided to make a widget class that doesn't have a pointer to implementation structure, and we aren't going to have a more efficient swap algorithm. So this widget node pointer is blueprinted here, and we just have the ints here being defined. So each one of these functions are passed in to do something, and do something. Think of it like a function that's doing a lot of different stuff, and a part along the way it's going to want to swap uh, these widgets and things. So for the first one, it's passing in widgets where we have a total template specialization for standard swap. So the standard swap will be used, and it won't find any global namespace swaps for widget objects. Now for the next situation, thing double, when we swap those inside of do something, go back up here, we do find a global namespace swap that is made for swapping things that are of template parameter type of double. So that this swap function that is thing double, that is produced by the template or by the compiler for swapping things doubles, is what will be used. Okay, and finally, and one other thing too is that if in doing the lookup for what swap to use, it'll actually first look for a swap that exists in the same namespace as the arguments, which in our case doesn't happen, but it's good to be aware of that. And then it'll look in the global space for a match of the swap function to be called. And then finally, with widget node pointer, we have a calling of standard swap. And once again, just to really hit home, what's going on. The compiler looks at a swapping of two widget node pointer classes, and it says, aha, I can pump out a standard swap function here without the template stuff, and replace the t's with widget op types. And that's in the final client code, or in the final program code, when it's called, that is what it's called. 1 second, I'm just going to get a drink of water. Okay. I want to do a bit of recapping because given everything that's going on, it's hard to see the bigger picture, And that's what I'll do now by diagramming out a little bit. So we have our pointer to implementation structures. And they're actually being composed of two different classes. And here's one type of class, and here, so these are I don't know how to write that out. Okay, so here is, in this section here, which goes across the page this way, is our class that holds the pointer to implementation. And here in this side is our class that holds our implementation object. And when we make the instances, which are represented by these vertical columns here, we make sure to hook up our p impls to point to the underlying objects. To get into why we're doing everything as we do it, let's fall back to what was reviewed in part 1, which is what happens when a copy assignment occurs. So let's say we're making this instance be equal to this one. So we got to do a copy, and we have to use our specialized copy functionality because we're using pointers. So what that means is that we redefined things in such a way so that when we do the copy, this object 1 over here, let's call it object 1, it doesn't get a copy of the object 2's pointer implementation, because that's a big no-no. You then have two objects pointing to the same underlying data. So it would be something like this, and that would mean that this one would point at the same data, and you don't want that in client code. That's just a recipe for bugs. So what we did in our first part was redefine copy assignment in such a way so that what happens is what is copied is the underlying object and not the pointer implementation. So this underlying object here is what is copied over here. Okay, so that is great. Now the thing though is when we're dealing with standard swap, and we want to swap these two objects 1 and 2, we're saying we're making a temp of 1, and that's going to make a full copy of the underlying object. Because we're dealing with p impls, we got to copy the underlying object. So, and then, just like I have explained, we're doing an assigning, or not A and B, sorry. We're doing 1 equals 2, and then 2 equals temp. So just like I explained, all of this stuff is heavy cost. So what we do is for swaps, we do what I've been explaining all along and showing how to implement, which is just a swapping of the p impulse, and that is it. Okay. The next thing to do, and the last thing of our journey here, is to show the swap being used in a bit more of a real life scenario. So I have a class where I'll show some of the code in a little bit, but I want to just show what's going on with it in my whiteboard here first. And I have a linked list class, and that basically has an object. It only has the linked list class itself. Only has a one member called first, and what first is it's a type that is of a pointer to node. Or actually, let me do this. It's a pointer to a node of type T, so we can make things be flexible and have any type be our value that's outputted by the list. So we have our first node, and the linked list class, the only member it has is first. And what happens is when we construct this guy or copy construct it or have items being pushed onto it, first we'll be pointing to the underlying data. And just to clarify, first is the same type as our nodes, so there's just like a blank spot in its value section. So first is going to point to this guy, which is the actual data, and then for our linked list structure, it's going to be a bunch of pointers to nodes of type T, or nodes that also have pointers to nodes of type T. So that is that, and you can just to make it look a little bit better, I'm going to add another one. So what goes on when we try to have another one of these guys like this? And we want to do copy assignment. Well, the way to do it that is not exception safe is to iterate through. Let's say we're trying to have our first linked list here be copy assigned to this next one. So the way to do it that would not be exception safe is to basically destroy our first list, and then to copy construct a new one off of our one we're trying to assign to. So we call the copy construction, and that what that does is it leads to having the first node pointer get copies like this, and it'll get its copies. So the issue is, what happens when one of these sub copy operations that's occurring leads to an exception. So what happens if, say, the exception is here? Well, then this one won't happen either. So what happens is we then have a linked list that's in an invalid state, and that's no good. We're not delivering on the strong exception safe guarantee. So what I'm going to do is just delete, or not delete, but hide that part, and I'm going to show a little bit of code here first. So prepare yourselves. Here's my linked list, and here's the copy assignment operator for the linked list. It is actually exception safe at a strong guarantee level. The reason why is because of this. We are making, right here on this line, we're making a full copy construction of what we're assigning from into temp. And then we're doing a swap between the object pointed by this and temp. And the swapping is following the same rules that we had before. And to preface as well, this is very similar to our pointer to implementation structuring. We have a pointer as being the only member for our linked list. So we're doing a swapping where what's defined to be the swap is just swapping the pointer to node of this and temp, and that the defining of it is down here. So you can see we're doing our swap functionality where the arguments being swapped are template derived. And what this does is really cool. It gives the strong exception safe guarantee, because we're either going to be in our original state for the linked list, or we're going to be in the state we want to get to. No in between, given exceptions occurring or not occurring along the way. So we have temp doing copy construction. So it's a linked list, so it's calling this copy construction here. So to diagram it, we have a temp being made, a temp linked list, and it gets a first pointer to node value. And what we're attempting to do is have linked list 1 be copy assigned to linked list 2. So temp is made, and it gets its address first member here, and then we do the same structuring like we saw before, and it goes through and does its construction based off of linked list 2's data, right? And then at this time, if any exceptions occur, L1's still in its original state, which is great. So now we have L1's first here, and once this whole operation happens, which is the first line in the copy assignment function, which is here. So this in the blue highlight is this happening, and then we do the section part, which is the swap. And as we saw, the swap has been defined to just do a swapping of the first addresses. So the swap happens, and now L1 has all of this data, and temp doesn't have that first anymore. Now temp has this data. And finally, as we're all probably wondering, the destructor for temp is called, and all the data, all the old data, let's kind of draw it behind our lines here. All that old data is successfully released. So there's a the destructor goes through and it destroys the data. It doesn't destroy it. It releases it to the memory wild. So that's it. Lastly, of course, this guy goes to. So that explains it all. I wanted to be able to show a unit test for this, and I can do it quick enough. Let's just do it. I want to be able to show you guys a little bit of unit testing. So I'm using Google Test. Here's some of the code for it. We are able to have a test class that initializes our data for the tests that occur. And we're initializing a linked list of type char called list1, and every time these tests are called, list1 reinitializes so that we have the tests not influencing each other. So here I am testing the pushback functionality. I am doing the pushback operations. So list1 gets F and then O and then O, and then I have a data tester function, which is defined here, which goes through and tests everything. Really quick covering also, this macro works in such a way so that the code inside of here is treated as if it's a part of the class code here. So I won't get into a full presentation on Google Test, but let's go ahead and make a new test. Works off of our linked list test class, a linked list test case, and we're going to call it copy assignment. Okay, let me just, I'm just going to go ahead and copy this guy. Okay. And we're going to make a linked list stuff, linked list type car called list 2. And we're going to have list 2 be equal to list 1, which uses copy assignment. We're going to use our data tester function to test that the data, which will be what is tested against here, will be tested against the data inside of list 2. So, you know, these values here will be tested against what was originally pushed back onto list 1 but has been copy assigned to list 2, so should exist inside of list 2. And then that function is called data tester, which iterates through the string literal, the pointer to character constant, and it expects equal the values pointed by each pointer. One is an iterator into our linked list. The other is just a pointer to character constant. And I'm doing a post increment add assign, and that is what we want. So I'm going to go ahead and save it, and let us. So what I did here is, so here's my linked list repo items, and I actually had to have this code now run off of Microsoft Visual Studio Compiler because that's the only thing that works with Google Test. So here's my, let me go grab it. Here's my my batch file. I'm making a build directory. I'm changing into it. Then I'm calling the various Visual Studio Compiler variables given the AMD 64 parameter. And then I'm calling CMake, which looks at the the instructions inside a CMake list test txt file here, and it produces a bunch of make files that are geared from Microsoft Visual Studio. And then finally I call nmake off of Microsoft Visual Studio, which works with those files, and then I call my linked list program, which has all the unit tests in it. So I'm going to go ahead and call it. All right. So we had everything happen. The creating of the make files, the compiling and linking, and then finally our tests, of which I just made the copy assignment test, and they all passed. So that's it. All right. thanks for watching. I know this was a long tutorial, but it's great to be able to look at a bunch of stuff that is different, but they all have meaning together, which is what I hopefully did in this presentation. So thank you for watching, and see you guys next time.